the chapter number 1. What you have to do, you have to first study about Coulomb's law. Obviously, Coulomb law, you know what is Coulomb's law. If there are 2-point charges q1 and q2 and they are separated by distance r, then Coulomb law said that the force will be proportional to the charge's magnitude and inversely proportional to the square of the distance between them. And then there is a constant 1 upon 4 pi epsilon naught. What this constant is? This constant tells us about the permittivity. This is the permittivity, that is how much the medium will affect the force. Okay, so if you say that if this medium is water, then in that case the force will be reduced by the factor. We have another term, that is the relative permittivity. This is epsilon upon epsilon naught. Basically this is a number. Okay, this is a number, and this tells us that how much time the force will be reduced. Okay, now the charges I was talking about. Okay, if I take this charges, okay, the same charges, the distance is same. If they were in earlier they were in a vacuum, okay, and there was certain force acting between them. Suppose the 100 force was acting between them. Now what happens, I take this two charges to water. When I take these two charges with water and the distance remain the same, okay, then I see that it has been reduced. So if suppose it comes out to 10, so it has been reduced by the factor of 10. So I'll say that the relative permittivity of water is 10 times 10. Okay, that means it is the force has been reduced, the electrostatic force has been reduced by 10. So this is relative permittivity. It has another name, dielectric constant. So basically in Coulomb's law, the force is being influenced by the medium between the two charges, unlike gravitation force, in which the force is not affected by the medium. Okay, and now we have what the next important topic is. Obviously a dipole is very important. And what is a dipole? You know, dipole are two positive equal and opposite charges separated by a distance. For example, in chemistry you have studied about HCl molecule. So HCl, you know, in this the electron are being shared, but the electronegativity of chlorine is greater than that of hydrogen. Okay, so this electron pair will be a slide towards the chlorine atom, and hence the chlorine will acquire a partial negative charge, and this will a partial positive charge. So this is a good example of a dipole. Okay, electric dipole to be precise. Okay, so what we have to do, we have to find electric field of due to dipole at an axial point. What is an axial point? This is a line joining the two charges. Okay, this is a direction in which the dipole moment. Okay, another term is dipole moment. First of all, I'll skip the topic, important topic. Before explain dipole, I have to come to electric field. Okay, I'll first explain electric field, that is important too. Okay, so what is electric field? Just remember that there is a charge. Okay, this charge will create. Okay, so if I take another charge, okay, this is first charge and this is second charge, I see that when I keep them this distance, this charge is not feeling any force. Okay, I not experience any force. Okay, but when I just cross this distance, I put it there, I see that it experiences a force. Okay, the field is basically the space around the charge, the vicinity of the charge around which another charge will experience a force. Okay, so what happens is, this charge has disturbed the surroundings or medium around it. Okay, and the disturbance, if I put that another charge in the region, that disturbance will exert a force and onto the second charge. Okay, so this is the concept of field and electric field. We can just what we can do, electric field intensity at any point. Obviously you see this charge and it is disturbing the different point with different magnitude. Okay, the closest point it has will be disturbed more. Okay, another way to say this is, if I keep the same force close to this, it will experience greater force. but the same charge if kept at a more distance from it will experience less force. Okay, so electric field intensity is more here, this point closer to the charge, and less here. How we give electric field intensity? It is just given by the force experienced by a test charge. Okay, so we'll just divide force by the magnitude of the charge. What is a test charge, by the way? So basically a test charge is a unit charge which has a very small magnitude. It is just to find the force experienced by a charge at a particular point. Okay, how much this point has been affected by this charge. So we have to place a charge, and it should not change the position of this original charge. So that was we have brought a very small charge, that is the test charge. Okay, so what is the magnitude of electric field intensity at any point? This is given by F upon Q naught. Okay, and for a point charge, if we derive it, it is not a very complicated one, because we'll just plug in the value of force in the for a point 2 point charges. Okay, and we know what that is. That is electric. That is just force magnitude 1 upon 4 pi epsilon naught Q1, Q2, and the second one was a test charge, obviously. So we'll just divide by the Q naught, because I told you electrical intensity is force experienced by test charge. Okay, then we'll just derive the test charge, and this will cancel out. So this is the magnitude of the electric field at a distance r. Okay, there will be an r square here. Okay, so this is the magnitude of electric field. What is the magnitude of electric field at a point r? This will be 1 upon 4 pi epsilon naught. Right, let me write it out more clearly. 1 upon 4 pi epsilon naught q upon r square. Okay, so now just when I coming back to the discussion of the dipole, so then dipole, this is a negative charge here, positive charge separated by distance. A distance we take as 2l. Okay, in another book someone says 2a, that doesn't, not a problem, but the thing is why we have taken 2l. Okay, actually we when we study the electric field due to this dipole at certain distances, from which point we will consider? We will consider from the midpoint of this dipole. So midpoint of the dipole will be here. Okay, so to make the calculation relatively easier, so what we do, we'll just divide the dipole into length into, this will be L and this will be L, so the total length will be 2L. It is just a convention, it will make things easier. Okay, so at axial point, that is here. Okay, how much will be the electric field? Axial point is the end-on position. Okay, just the line joining the dipole, the two charges just extended, we get the axial point. How much is the electric field here? Okay, so remember, for a short dipole, okay, this will be equal to 1 upon 4 pi epsilon naught 2p upon r cube. Okay, very important formula, and the derivation is also important. Okay, and what is this p here? The p here is dipole moment, electric dipole moment. Just a second. P here is, what is p here? This is electric dipole moment. What is this meaning? What the meaning of this electric dipole moment? Okay, so basically it is telling about the strength of the dipole. Okay, and another, I'll go to another topic from here. Okay, so if there is electric field, okay, as I told you, I can repeat again what is electric field is. Electric field is, obviously this field will be due to a charge. Okay, it will disturbing, and the parallel electric field, that is uniform electric field. Uniform, that is the value of electric field in all this region is constant. Okay, if I have to assign a value, I'll say 4, it is 4 here, 4 here, 4 here, everywhere it is 4. So this is uniform electric field, and it is denoted by parallel lines. Okay, parallel lines that are called, another thing, another topic has to be mentioned here, electric field line. Basically they are a representation of electric field. Okay, so this is a represent here. And now uniform electric field, if I place a dipole here, what we see, this dipole, it will experience a torque. Now you have to know this torque from class 11. Okay, what a torque is. Okay, so if I'll give an example for this. When you're opening a water bottle cap, what you're doing, you're rotating it. Okay, you're exerting force on the bottle, but is the force acting on the bottle cap, it is making a translation motion, that is moving it in a straight line? You say no, it is not moving it in a straight line. Then what it is doing, it is making it rotate. So the rotating effect of force is called torque. Okay, similar to here, when we place the dipole in the electric field, what we see, that this there are two, obviously a dipole is consisting of two charges, 2 point charges, and we can study them separately. Okay, so another discussion is there. Okay, I'm just going through the small details when mentioning the important topic, and I just have to go to the important small topic that are also important that you need to understand. Okay, so what if I say there is a negative charge? Let's take positive first, that will be easier for you. Okay, so now this electric charge, positive charge, is placed in a electric field. So what will happen to it? Obviously the field will exert a force on this charge. As I told you, a charge creates an electric field, and that electric will exert for another charge. Okay, so now this charge will experience a force. So my question is, in which direction the force will be applied? And I'll just first, let's not include mathematics here, not the formula, just have an intuition. So this charge will experience. Okay, so you see this electric field, what is the direction of electric field? Positive charge will have electric field in the outward direction. This is the convention we are following. Okay, so negative charge, if positive is exerting electric field outward, okay, obviously negative is opposite, so it should be inward in this direction. So if if I face another charge, it will experience charge outward. Okay, so if a charge plays an electric field, a charge plays an electric field, in which direction will force will applied? This direction, in the direction of the electric field. Now come to the formula. Now you see electric field was given by, electric field intensity was given by F. Let me include the vector here because we are concerned with the direction too. Okay, so this is the formula for the electric field, and just cross multiply it, what you'll get, F is equal to QE. Okay, so now this charge, if there is a charge and it is an electric field, it will experience this much force. Magnitude will be charge, magnitude of charge multiplied the electric field intensity. Okay, and we were concerned about the uniform electric field, so it will be a constant. Okay, though this is the magnitude of like force that the charge will experience. Okay, what about the direction? In which direction the force will be applied? Okay, so you see electric field, and this is the vector. There is the positive sign here, positive charge, so the force will be in the direction of the electric field, as we discussed earlier. Mathematical. If there is a negative charge, what the formula says, negative. In vector, if there is a negative sign, okay, so that means this force should be in the opposite direction to the electric field. So if a negative charge is there, in which direction it will, it is a field here, and there is a negative charge, in which direction the field will exert force on the negative charge, it will in the opposite direction. Okay, so now what is happening in a dipole? Let's come back to dipole now. Okay, this electric, it was placed in a electric field. Okay, it was placed in a electric field, and this electric field, what was it doing? There was a dipole placed. Let me use another color for this. Okay, let's take this color. Okay, so now there's a dipole here. Wait a second. Okay, so now yes, this will be okay. So dipole is here, negative and positive. So electric field, the force on the positive will be here and the force on the negative will be here. You see, there are two forces. Okay, what will be the magnitude? As we know, the dipole is having equal and opposite charges. What about the magnitude of the two charges? Suppose this is of 10 magnitude. How much will be the other one? Yes, 10 magnitude. Obviously it is negative, the sign will be opposite, but the magnitude is same. So the point is, force on this two, and the electric field is constant. Electric field is constant, F is equal to QE. So the force on these two charges will be what? The force on the two charges will be same, but the thing is they will be in opposite direction. The force on this will be in this direction for the positive, and for the negative it will be here. Okay, you see, the two forces are equal. Suppose say 20. Are they in the same direction? No. Are they in the opposite direction? Yes, they are in the opposite direction. What will be the resultant force? If two forces of equal magnitude are acting on a body, how much is the net force on a body? Okay, it is very clear, very simple. Okay, suppose you are being pulled by two person. Both exerting same force on you, but both exerting it in opposite direction. 10 newton on one side, 10 newton on opposite side. How much net force will you experience? Zero net force. Similar happened to dipole, because the same force is acting on opposite direction. The dipole will not experience a force at all. So what will happen? No translation motion. But the catch is, this dipole, the line of forces, you see this, the force, the line in with the first force at this line, and the line in the second force at this line, are they same? No, the line is not same. So this is the reason there will be a torque. Okay, there will be torque. This will be act as a pivot point. Okay, pivot point, the fixed point, and there will be two torque acting, first due to this, first due to second due to this, and they will consider a couple. Okay, two equal parallel forces acting on the same body having different line of action, they constitute a couple. Okay, it is similar to opening a yes, it is similar to opening a ball. There was a, let me rub it first, just a second. Yes, okay. mm, hmm, okay, yes. Yes, to you see, when I was talking about that cap of a bottle, there was a force acting by a thumb. You are acting force here, and by a finger you are acting force on this side. So it was creating a rotation effect. Similar here, rotation effect will be created. Dipole will be rotated. Okay. So now what happens is, it will be rotated. How much force it will experience? How much force will it experience? Okay, so it will be experiencing a force. Okay, the force it will be experiencing will be a torque will it will be experiencing will be. And what is the formula for torque for a couple? It is force, either force. Okay, they are exerting equal forces multiplied by the distance, perpendicular distance between the two forces. Okay, what is the perpendicular distance between the two forces? This is minus q, this is plus q. The force is here, second force is here. Their perpendicular distance will be somewhere. This is the perpendicular distance. How much is the perpendicular distance? This is the perpendicular distance between the two for this line. Okay, suppose this is making theta angle with the electric field. Okay, so clearly, and this, this is 12, I told you earlier. So how much it will be? From trigonometry we can easily find this will be 12 sine theta. Okay, so how much the perpendicular distance? This is 12 sine theta. So coming back to what we were doing, just a second, wait for. Yes, so what will be the force now? So it will be torque will be how much? This will be either force multiplied the perpendicular. I told you this is 12 sine theta. and force is how much? It was QE. As I told you, the force exerted by each charge will be this much in magnitude, 12 sine theta. And this quantity you see, Q times 12, this is dipole moment. What is dipole moment? I told you earlier, I'll repeat it again. P sine, first let's derive this formula. So torque is how much it is coming, its torque is P sine theta. And in vector notation we can write, this is torque is a vector P cross E, this is the cross product. Okay, so this is the formula for the torque acting on a dipole with dipole moment P and placed in electric field E, uniform electric field obviously. What is dipole moment? Let's understand it more deeply. So what is happening is, okay, so I have to see there are different okay, first arrangement, there is electric field. First of all, let's just make electric field here. Okay, so now what happens is, just a second, yes, so there's an electric field, and what I did, I just in this electric field I put a dipole. Okay, this is dipole. The charges are 10 or 10. Two charges are there of equal magnitude of the dipole, minus 10 plus 10. Okay, now tell me, if there is another dipole with magnitude 20 and 20, the length is same, which dipole do you think will experience more torque? You will say that this two charges will experience more force, because force is what? Charge times the electric field. Electric field is same, charge is more, so this two will having more force. And if there is more force, then the torque will be more. So the strength of this, okay, how much this electric field is acting torque on this depend on the charges. So this strength of the dipole, this is the strength of the dipole. It has more strength. Okay, how much more it will be rotated. Similarly, if I take, and the strength depends on the charges, magnitude of the charges. Another example, and there is a one dipole. Now we'll just take 10 charges, minus 10 plus 10. Similarly, there is another dipole, minus 10 plus 10. And length, however, is different. It is double the length of this one. You can see this. Which dipole do you think will be rotated more? Just guess, make a guess. Obviously this one, it has longer length. Let's just compare this, take an analogy for that. There is a water here. Okay, imagine the electric field is replaced by water, and there are two sticks. One stick is double the length of the first stick, and they are placed obliquely in the direction of the flow of the water. Which stick will rotate more? The longer stick will rotate more. So similarly here, this dipole with a longer length having the same magnitude will be rotated more. So the rotation will be more. The strength of the dipole, it depends on the length of the dipole. So we made a quantity, strength of the dipole. Okay, that depends on two factors: the charges of the dipole and the length of the two dipoles. That quantity is the dipole moment. Dipole may basically tell the strength, how much the electric field rotate the dipole. More the dipole moment, more torque it will be acting on it. Okay, and so this is the strength. Okay, so coming back to the formula that we had devised, this is torque P cross E, or in the magnitude wise it will be P sine theta. Okay, now theta can be different in different cases. Okay, so the dipole is arranged like this, the electric field is there, and just remember dipole moment is from negative charge to positive charge. Okay, this is the direction of the dipole. Okay, now what is the angle between the dipole and electric field? Electric field is here, dipole moment is also in the same direction. The angle is theta is 0 degree. So just substitute theta in the equation of torque, you get sine 0 is how much? 0. So 0 torque we acted. So when dipole is placed perpendicular parallel to the electric field, such that the dipole moment is in the direction of electric field, the torque acting will be 0. This is a minimum torque. Okay, and we'll say understand earlier when we discuss about potential energy, this will be the minimum potential energy. It is the case of stable equilibrium. Okay, that we can understand only when we have the knowledge of the potential energy of the dipole. Okay, now if the theta is 90 degree, dipole is like this. Okay, and here the cosine 90 is 1, so torque will be P, and this is the maximum torque experienced by a dipole. Okay, this is an important question, just you have to remember this condition. And if I take the dipole to be opposite like this, in this case you can see the dipole is making dipole moment is from here to here, negative to positive. Okay, it is opposite to electric field. The angle it makes with the electric field is 180 degree. And what is 180? Sine 180. Sine 180 is -1. Sorry, not -0, that is cos 180. Okay, so this is torque is equal to P 0, that is 0. Again there will be 0 torque, and is a case of unstable equilibrium. Again, unstable equilibrium will understand only we have the knowledge of the potential energy, that we'll discuss in the potential energy chapter, that is the second chapter. Okay, so that's it. We have done an important thing here about the dipole, and these three conclusions are very important. Now have we done everything with this? Okay, no, a portion remains. And then thing is, we are physicists. Okay, we are just studying physics and we just want to experiment. We are not satisfied with one way. Okay, aren't we don't see things. What's the beauty of physics? The beauty of physics is everyone has a different perspective of things, the laws. Not everyone sees the thing like the same. Okay, if it was the same, then physics would be boring. Okay, so a different person, Gauss, is what he does. He sees electric field in a different sense. What is the electric field as? Okay, he introduced a term. Okay, electric flux. What is electric flux? We have a very important topic again. Okay, this has been used important in itself and being used in different chapters, and it will come again and again. Okay, so you have to understand it very well. Okay, so electric flux is basically, okay, I'll just give you an example for this. Okay, so there's a river flowing here, and there's a ring here. Okay, a ring. Remember, inside the ring it is empty. Okay, open. So how much water will flow? Okay, I have to measure the water flowing through this ring. It will be more when I place ring here like this, or if I place the ring like this. Okay, so you will say obviously this will be more open. This open surface of the ring will be more facing more water level in this position, so more water will be entering through it, rather than this. The water is just moving over it. Okay, so more water is flowing, more volume of water is flowing through it. Okay, so this is flux, this is water flux. Okay, so basically what is flux is the amount of a substance entering through an area. Okay, so now come back again to electric field. So electric field is here. Okay, and we have an area. Okay, again you can take an area like this or another portion like this, making a theta with it. Okay, so we want concern how much electric field, the volume of electric field, amount of electric field passing through the area. So, and it should be the electric field we will passing, which obviously those electric will be passing that is normal to the field, normal to the area. Okay, so what we do, flux we defined as electric field, number of electric field lines. How do we measure electric field? We measure it by the number of electric field lines. So electric flux is number of electric field lines passing through a normally through area. Normally, just remember. So flux definition will be, formula will be E dot okay, if there's, I'll just take a simple case. Okay, uniform case, uniform area, E dot A or E A cos theta. Okay, why cos theta? Because we are concerned with the only those electric field lines which are perpendicular to this area. Suppose the area is tilted here, so we have to take which electric field. Either we can take the area vector area this, the we can take the component of the area perpendicular to the electric field, or the better will be just take the electric field component of electric field perpendicular to uh, this area. Okay, which the electric field is here, so the perpendicular component will be through this area will be E cos theta by simple trigonometry. So this will be flux will be how much? Ea cos theta. Okay, this is flux. Okay, and what is it is? It is the amount of electric field entering through an area. Okay, and you can guess from the formula in which case it will be maximum. It will be maximum as I told you about the ring. Just remember the example. It will be maximum here. So if I ask you what is the angle between the area vector and electric field, and don't get it wrong, it is not 90 degree. It is not 90 degree. You will say that it seems like 90 degree. Why is it not 90 degree? I'll tell you why. Because just imagine what is area vector is. Area vector is something like this. Okay, the area vector is the vector. The unit direction will be perpendicular to the surface. The perpendicular to the surface is this line, this vector, and the electric field is also here. So how much angle this is making? This is making 0 degree here. So this, what is the flux in this case then? This will be Ea cos 0. And how much is cos 0? It is not 0, it is 1 maximum. So flux in this will be maximum here. It is Ea. What about that orientation? This orientation of the ring? Okay, and we know that none of the electric field lines is passing, or the water in the earlier case is going through it because it's flowing straight, so it is 0. And obviously from the formula you see it is Ea cos 90, and how much is cos 90? It is nothing but 0, so no electric field line is passing through the area. Okay, so we have got an idea of the flux, and now we're ready to see electric field in a different way. Then we see it as that is called a very important law, and it also a part of the Maxwell equations. Okay, there are 4 Maxwell equations. So what is Gauss's law? Basically, so Gauss's law, first of all we have to understand a term, Gaussian surface. What is a Gaussian surface? Gaussian surface is a closed surface. First of all, it should be a closed surface. Okay, second one, it should be passed through the. It will be more clear if I tell you why we are using Gauss's law. Why is the need of the studying electric field again? We have understood electric field and we know the formula. Was a need for studying it again? Yes, there is a need. Obviously, there's a need, there's a reason. That's why studying it. The reason is it will make things easier for us for calculating electric field sometime when the it can be challenging. Okay, so but if you see later that Gauss's law makes things simpler. Okay, in at least in the cases where the things are symmetrical. Okay, so we will able to calculate electric field through Gauss's law very easily. It will make like very easy for us, obviously for some cases, but we are concerned with those cases are very important. Okay, so Gauss's law, that's why we are studying Gauss's law. Okay, just come, let's study Gauss's law. And okay, again, so I was talking about Gaussian surface. Okay, so Gaussian surface is a closed surface. It can be anything, any surface, any closed surface. It could be uh, a cube, a cuboid, a cylinder. All are closed surfaces. Okay, and now, and it should be closed. I told you and it should. Okay, now just come, let's calculate. Let me define Gauss's law. That is, there is a charge here. Okay, there's a charge here Q, and I have enclosed this in a Gaussian surface, a closed surface. So this I have enclosed, put it in a box. Simply stated, put it in a box. This charge had been trapped in this box, inside it, not touching the boundaries of it. Now if I ask you how much electric field lines, okay, how much electric flux rather, the amount of electric field is passing through the whole of this box. Again, how much electric field is passing through whole of this box because of the charge. Okay, so this charge will not do any partiality with any side. It will just make electric field, produce electric field in all the sides, all the directions. Okay, and we can, when we derive it, we come to know that the charge, the electric field, the electric flux rather, what was electric flux? It is the electric field lines passing through this area. It has 6 faces, 6 areas. Okay, so how much that electric flux, the electric flux was given by E, or in that case what we can do, yes, integration of close integration of E dot ds is the flux. Okay, total flux, we just multiply the small area with the electric, this is the small flux, and for the whole surface this is the closed integration. We have just joined or added all the flux to all the sides, 6 okay, it will be different for different situation. For the case of Q, the 6 okay, let's break it down the formula even more. Okay, for the case of a cube, the charge will be, what can I do? I can have to find electric flux to this point. Okay, so I take this area of this point ds and multiply the electric field intensity with the area. Obviously normal component, that is be E dot ds vector, or eds cos theta, and we have just added the integration, that added all this. There will be a number of infinite number of points like this, and I just added all the flux and I obtained this for one side. There are another side like this, there are 6 sides. Okay, 6 faces, 6 sides. Okay, 4 walls and 2 upper and down rectangles, and when I added all those, there will be close integration of E ds. That's how I obtain the flux. What is Gauss law? Says this flux is 1 upon epsilon naught times the charge enclosed. Okay, so let us just think about why this things comes here. Okay, first of all, let me ask you, the electric field is affected by the medium. Yes, we have discussed earlier. It is the force is affected, electively affected by the medium. It is not gravitational force. Gravitational field which not be affected by the medium. It is indeed affected by the medium. So this epsilon naught tells about that. The electric field is flux passing is medium. Different medium, the flux will be different because the electric field will be different. Okay, and also the charge enclosed, replace the charge with another charge, and you see the electric field is different, so the electric flux is different. So hence the verification of the formula. Obviously it is not a derivation, I'm not concerned about a derivation, that is not important at all, but I'm just giving you the thing that we can justify the formula. Okay, the flux depends on the medium, and that is been told us by the epsilon naught and a charge inside the Gaussian surface. So let's come back to the Gaussian surface. Okay, so now we have to find the electric field due to this line, infinite long wire. Okay, infinite long wire, it is a very long wire. Why infinite? That's a good question actually. Why infinite? I'll answer it. Let me first find electric field due to this line charge. It has a charge, okay, all over it. It is a line, a wire. Let's take a wire, very small width. Okay, it is of infinite length, and I want to find electric field here at r distance from this wire. So how can I do it? So for that I will take the help of Gauss's law. Okay, so what, as I told you, we have to draw Gaussian surface, and when I draw Gaussian surface it will be like this. It should be closed, a closed cylinder I take, and it should pass through where? It should pass through that point where I have to find the electric field. Okay, so the second condition of the Gaussian surface is it should be closed. It should pass to the point where I have to, the point is suppose here, to the point we have to find the electric field. Remember why we are using Gauss's law, to make things easier, to find the electric field easily. Okay, so this is the point. And now third condition is also there for Gauss's surface, that is it should be symmetrical. Okay, that is the most crucial thing. If it's not symmetrical, then the whole purpose of using Gauss's law is gone. Okay, symmetrical. The you see that for this curves area, you see this all cylinders, spheres, cuboid, cubes that we study in mathematics in lower classes. Okay, they are symmetrical cases. Even up to higher classes we study most of the thing. Obviously we are also concerned with non-irregular shapes, but these are the regular shape, they follow symmetry. Okay, so in the whole this curved region there is a symmetry, and also in this upper and lower circles there is symmetry. So what we can do, we can dissect, we can think of this solid cylinder as three symmetrical surfaces: on the curved surface and the up and down circles that are also three symmetrical surfaces. We can find out electric field, electric flux for these three surfaces separately. Okay, now you see how to apply Gauss's law to find electric field. There are steps, three easy steps. Remember the step for one shape, one figure, one case, and just repeat it for the everyone. So it's like the algorithm, not algorithm, uh, just three steps and you can just apply it everywhere, it is the same. So first what we have to do, we have to draw a Gaussian surface. Again, Gaussian surface should be symmetrical, close, and it should pass to the point where we have to find the electric field. I've done that. Okay, now second point is let's calculate the electric flux. As I told you, electric flux, I can see, I am able to see this Gaussian surface as three symmetrical surface. This curved surface, this through two circles. What is the electric field at this point for this whole Gaussian curved surface? It is here. It is here. Okay, the electric field is perpendicular to this curved surface. Why? Because of this charge. You will say it is also here due to this charge too. Due to this charge it is here. Why you're not taking those? Okay, that's a good question. If you see NCRT, you see that explanation is given. I can what I do, I can resolve this as like this. This electric field I can resolve like this in two components. Okay, for this there is another charge here, and I can resolve this like this. Okay, so you see this two will be cancelled out. For each component here there is another charge here, and that will be cancelled out. So this factor, these lines are cancelled out. So what I will get, only the electric field in this direction, horizontal direction. So now this the infinite thing, I told you that I will explain why we have taken infinite. That this been clear here. If it is was not infinite, okay, if the wire was not infinite, okay, so for you see electric field here, okay, the electric field will be due to this positive, it will be here, and for this positive charge it will be here. Will this be, and I can again resolve it into two components like this and this. Will this component will be cancelled out? Okay, you see there is no positive charge here, which can produce electric field like this and cancel this electric field. So our causes, what we are doing here in this derivation, will not be valid here. Where? At the ends. Okay, so that's why we have taken infinite case. Okay, then it will be only valid. So it is not valid for non-infinite, for a finite length rod or a wire. It is actually valid, but not at the ends. In the middle, it will do perfectly okay, but in the ends, the things will not go as we expect with the Gauss's law. So that's why the approximation, and we can just take care of the middle region, okay, for a finite rod too. So let's get again to that thing where we're discussing. So this is positive, and again Gaussian surface we have drawn. Three parts. Electric field is here. Okay, no worry about this and this electric field. Electric field is here. For this small region, let's take this is a very small area. What is the area vector? It is also in this direction, perpendicular surface. What is the angle here? 0 degree. So what is the flux here? It is E ds cos 0. That is 1. Okay, so and if I have to find the flux, this is due to a very small point in the curve region. If I have to find the flux due to the whole of the curve area, what I can do, I just add those all areas and I just integrate them. Okay, I'll get this flux. Okay, so this is the flux due to the curve part. What about this two circles here? You see again the electric field is here, direction electric field here. If I take a point here, ds, it will be, what is the area vector? It is always perpendicular to the surface, so it should be here with ds, say ds2, electric field here. How much is the angle between them? That is 90. And what is flux? It is eds cos 90. How much cos 90 is? 0. Problem is solved. No flux through there because the electric field is not here, it is here. Okay, so only electric field is in this region. Okay, flux is through this part only, the curve part. And how much was that? It was eds. Okay, and because the total electric field in the upper and lower region is 0, so I just can take the total flux to the whole of the surface, Gaussian surface, is this much, close integration. And now just come to this was the second step. This is the electric flux to the this Gaussian surface. Third step. Now apply the Gauss's law. What is Gauss's law? Gauss's law is simply the flux is 1 upon epsilon times the charge enclosed. Charge enclosed was, now the question, another thing comes in, charge enclosed. How much is the charge enclosed? Okay, so for charge enclosed, this was the infinite charge line. Okay, now let's, I always give this example of the shopkeeper vendor. I don't know, I just don't go shopping and buying vegetable, but this example I use a lot in the situation, and it helps me to understand, and surely it will help you. Okay, so when you go for buying vegetables, what do you ask the vendor? Yes, the rate at which the vegetable is being sold. He told you that it is 30 rupees per kg, and if you want to buy 3-4 kgs, you just multiply by the rate with the number of kgs that you have to purchase. Okay, 30 into 4, 120 rupees. Okay, simple math. Again, that I apply that knowledge here. There is an infinite long rod, and it is uniformly the charge is spread uniformly. It is same everywhere. Okay, now see, if I told you that the charge in a very small length, suppose in 1 centimeter, it is 4 charge, 4 coulomb in 1 centimeter. Okay, and I just Now I have given you that key, the rate, and if you want to find the cost of any length or cost of any number of vegetable and the number of kilos of vegetable, you can do easily. Similarly here, the charge of any length you can find out. Just multiply this thing that I have given, the secret recipe that I have given, just multiply with the length. And this is a name actually. It is called lambda. And what is lambda? It is a name, linear charge density. What is linear charge density? As the name suggests, linear is for line, charge density. Okay, how much charge is for in the per unit length. Okay, here in the example I told you 1 centimeter, 4 coulomb per centimeter. Okay, so lambda, we will given lambda for our problem. And you see the cylinder I have drawn. Okay, this is of, suppose this is of L length. Okay, so how much charge will be in this charge density is for the 1 centimeter, the charge is lambda. That was the linear charge density. Just multiply with the length. This is the charge enclosed. Okay, so the everything is been plugged in. So uh, in this what I can do, let me do it. Okay. Okay, so the I'll just we were done with like this ADS, and this was 1 upon 4 not 1 upon, yes, 1 upon epsilon naught. Q enclosed was lambda L, we have find out. Now let's do this, the electric field for this region. Okay, because the charge is, and you see, yes, uh, yes, the electric field here, it is constant everywhere. So we can just take out from the left hand side, we can take out the this E outside of the integration, because it's constant everywhere for all the surface. What is the integration of ds? Okay, this is ds is basically what, the curved surface area. And what is the curved surface area of a cylinder? You know, it is 2 pi, and the height here is L. Height here is L, as I told you. So 2 pi RL. So now plug it in the what we have got. I'll write it again. This was E ds, integration of ds, charge enclosed was lambda L upon epsilon naught, and this was, we are getting 2 pi, let me write it more clearly, RL is equal to lambda L upon it was epsilon naught. So L and cancel out, so we have the final expression. Obviously it is in terms of magnitude, lambda upon 2 pi epsilon naught R. Okay, very important. And you see there are certain conclusion we can draw. The electric field here, you can see, is depend on the length of the point. More the distance of the point where we find the electric field from the linear line charts, the electric field will be less. That is understood. It will be further, so electric field will be weak there. Okay, and what is direction? Direction is obviously for positive charge. For positive charge, the electric field will be, for the positive charge, electric field will be yes, electric field will be outward. Okay, for a negative charge, if it was negative charge, then in that case electric field will be inward. Okay, so these are the two cases. Okay, so this thing you have to just go through it, and you can do it for a yes, for a surface charge density. Surface charge density you can do. Okay, so what is a surface charge density? It is a infinite sheet of charge. Okay, infinite sheet of charge, and just copy paste everything from there. In that we needed lambda. What was lambda? Linear charge density, charge per unit length. Here will we need charge per unit area, that we have a name that is very popular for memes, sigma rules. So here it is sigma. Sigma is what? It is charge per unit area. Okay, how much charge? Unit area 1 centimeter square is how much charge? Just multiply with the area that you need. Okay, again, so I'll just give a shortcut of this. Okay, in a short I will describe. For this positive, what we do, we again make a, we will like draw like a sheet like this. We again make a Gaussian surface. There is no hard and fast rule that you have to draw, take Gaussian surface like that, but a condition, it should be symmetrical. That will make things easy. It should be symmetrical. You can take any surface. So here again I am taking cylinder like this. It is passing through here and it is also passing here. Okay, I didn't expect it to draw like this. You will say that this drawing is not good. For my level, it is a masterpiece. Okay, so this is, the charge is here. Okay, and yes, electric field will be here. I will not explain everything. Everything is almost same. Okay, it will not be, direction will not be here. Okay, so and yes, this cylinder should be regular. Okay, so this area, if it is a, it is a, it is also a. Okay, so how much flux? Again, we can divide the Gaussian surface in 3 parts. This first region that I have, this is first region. Second region will be the curved surface area, and third region will be here. Okay, and electric field is in this direction, in this direction. Okay, and what about the upward part? The electric field again is here. So clearly an area, if I take a point here, the area vector is outward, upward, electric field is this direction. So what is the angle? 90 degree. So clearly electric flux for the that curved part of the cylinder here is 0, cos 90 is 0. So what is electric field remains for this region, okay, and this region only. Okay, and how much flux will be there? Electric field multiplied by the area. Okay, so this will be EA for one side, EA for second side. This is the flux for the total flux for the whole Gaussian surface. How much? 2EA. And what is the formula for flux from Gauss's law? 1 upon epsilon naught times the charge enclosed. Again, remember the 4 case in the linear chart, and that was lambda. In this case it was sigma A. Okay, sigma rule rocks. Okay, so just equate the two equations. So how much will get? 2A up is equal to 1 upon epsilon naught sigma A gets cancelled out. So what I get is equal to sigma upon 2 epsilon naught. Very important, very important. Why I'm saying very important? When you study capacitor and parallel plate capacitor, it will be used. So it is very important. Okay, electric field again for positive. Oh, I am drawing sigma is not a vector, man. This is sigma upon epsilon naught. This is okay. Obviously this is for a thin sheet of chart. If it is a thick sheet of chart, then 2 will disappear. Because in that case it is a thick sheet only. We have to draw Gaussian surface like this. Okay, so electric will be only this direction. 2 will disappear. Let's move further. If there is a, because you have to take capacitor further, and okay, there is a positive charge plate here, infinite again, and now it is very easy. If you know the formula, it is very easier. If there are positive charges here and here, infinite sheet of charge, electric field due to this will be here, for this, here and here. How much electric field due to this region? We have calculated. This is sigma upon 2 epsilon naught. It can be different, sigma 1, sigma 2. I'll taking the easy case. Okay, for this again here is will be sigma epsilon. Because of the first, let's make it first region, second region and third region. For the first region, the electric field is only this much. For the second region, it is how much it is? No. Okay, first, this is for because of the first sheet. Okay, first sheet, the electric field is here, it is sigma upon epsilon naught. Here it is sigma upon epsilon naught, and here it is also sigma upon epsilon naught. One thing I have missed, Okay, I'll tell you later what I missed, the distance thing. Okay, let me complete this first, then I come back to that. Selective field, what is the selective field? Okay, I don't want to confuse you, so let's sigma 1, sigma 1, sigma 1. What is sigma 1? This is electric field at the 3 region due to the first sheet of charge. Now due to the second sheet of charge, electric field in this region will be sigma 2 upon 2 epsilon naught. Here again sigma 2 upon 2 epsilon naught, and here it will also be sigma 2 upon 2 epsilon naught. Okay, if you see here, if you see here, electric field in this region due to this is also this side, due to this is also this side, they will add up. In this region they will add up, but in this region they are opposite, so they will cancel out. So what we'll get for the first region, they will add up, so will be sigma 1 upon epsilon naught my plus sigma 2 upon 2 epsilon naught. What if the two surface charge density are same? They are equal charge in the two bodies. They are the same area. Okay, then in that case, it will be only sigma, and it will add up to sigma upon epsilon naught. This is a special case if the surface charge density on the both sheet are same. For the second ether, we have to subtraction, so sigma 1 to epsilon naught minus sigma 2 to epsilon naught. Here I am assuming that sigma 1 is greater than sigma 2. And what if the two surface charge density are equal? Then they will be equal, and this will be 0. And the third reason, that is again very easy. For the special case, it will be sigma upon epsilon naught. So what I can conclude is, if there are two charge sheet of equal sign, okay, then it in this region, first region, it is sigma upon epsilon naught. Again special case, surface charge density are equal, then it is the case, it is 0 and it is sigma upon epsilon naught. Same is true if the negative charge are there on the both sheets, but that is not important is this case. But if you understand that case, things are very easy. This is positive, this is negative. Okay, now just use common sense. Electric field due to this, again first, second, third reason. Electric field due to the first sheet, it will be outward here. Okay, and in this region it will be there, in this region this will be there. How much this will be? Okay, sigma 1, let me do it later because I'm not able to write it, it will not clear. So this is due to E1, then just remember direction. Due to E2, the second sheet, it will be, now important, this is positive, so this will be outward, that's why I have done direction. For negative, you see the electric field is towards it, the negative field, E2. Okay, this is E2 is here, because electric field towards a negative charge, and either is also E2. So now just tell me, for the first region, are they in the same direction or opposite? You can say they are opposite. In this region, second region, they are same direction, and third region opposite. So for first region, this will be subtraction, sigma 1 upon 2 epsilon naught minus sigma 2 upon 2 epsilon naught. Obviously again taking sigma 1 greater than sigma 2. If they are equal, sigma 1 sigma 2 are equal. If sigma 1 sigma 2 equal, then it will be same 0. Okay, if third region, the condition is same. Okay, for second region, they were in the same direction, this, so they will add up. So electric field will be how much? Sigma upon 2 epsilon naught, sigma 2 upon 2 epsilon naught. If they are equal, then it will be sigma upon epsilon naught. This is a very important thing. For a two charged plates having the opposite sign, electric field is 0 here, electric field is 0 here, but in the region in between, it will be sigma 1 epsilon. Mighty useful, because capacitor is totally different. Parallel plate capacitor, we will use it you will use it, just remember this result, just remember this. Okay, and if you go through derivation very well, I don't think there's a need to remember this part. Only the starting was important. It was hard to understand. This part is very easy. Okay, just remember the result. One thing I missed was, like, for a parallel sheet of infinite parallel sheet of charge, the formula coming to be sigma 1 to epsilon naught, is it dependent on a distance? And we can see from this formula it is not. So that means that if we go any point, it, remember, it is an infinite sheet. Okay, infinite sheet, not drawing is small, it is an infinite sheet. That is only that, in that case the formula will hold. Okay, so you are saying that take a point here, p1, take a point here, the electric will be same in these 2 points. Yes, that is right, it is same in these 2 regions. But how can it be the same in this region? Earlier we seen the linear charge density case, it is different for different points. Okay, it is proportional, inversely proportional to r, but here it is not the case. It is same for both the points. How can it be? The answer is, just remember, just look at it. Like, okay, now it is a big infinite sheet, very big. If I go there, okay, very close to the field, to the sheet, okay, the electric field at this point is due to which charges. Okay, just you have to just assume, okay, let yourself go near a wall. Okay, if it is a very big wall, that will do it very, you will understand better. Okay, just go near a wall and keep yourself attached to the wall. Okay, and try to see, try to make a don't do it with a, okay, just imagine, if you do it a pencil, I don't know, you will make the hell of your wall. So just move your hand. Okay, hand, or try to, no, just move your hand and make a circle. There is a certain distance you have covered. Okay, now, so, okay, like you are covering this much distance. Okay, now go back some distance. Now see how much thing, again make a circle, and you see that you are, and in that case you were able to see only without moving your head, obviously. So you are able to see only this region, very small region. But when you go back, you see this much bigger region of the wall. What I'm trying to suggest here is the charge, when I end up very close to the infinite sheet of charge, and I'm very close to the infinite sheet of charge, what is happening? Only this charges, this field of view, the charges in the field of view of this point. Okay, this, when you're trying to see the things in the wall without moving your head, only these charges will be in force, or they will exert the, create the electric field, because these charges are very far, or not in the field of view of this point. This is very close, obviously. Okay, so they will not have any effect. So electric field will be only because of these charges. Okay, this small region of charges, this charges for the very close point. But when you go farther, the field of view increases. Now the field of view is like this much charge are exerting force. So because the number of charges are increased, the electric field should increase. So the point for farther away, because of the field of view of increase, so the electric field should increase. But the distance has increase, so distance increasing, electric field will decrease. Okay, electric field is inversely proportional to distance square. Okay, one factor is increasing the electric field, the field of view thing, and the other distance is decreasing. So the overall result is one factor compensate the other factor. So the result is there will be, electric will be constant. Okay, I think you got it. Okay, it's a big video. I thought that I will just experiment to teach like this, and it's been a long video. So just if we read it, we have almost covered most of the important part of the chapter. One thing remains, um, for a spare, okay, or a conductor, hollow conductor, okay, even solid conductor will do, and a hollow shell if it is insulator hollow shell, okay. In these three cases, charge will be on the surface. For a solid sphere conductor, charge is on the surface. For a hollow conductor or insulator, there is no way it can be in the empty space, it is on the surface, okay. For this, again we can apply Gauss's law. Just do it as a homework. Try to imagine a Gaussian surface, again cylinder will be do it perfectly. So in that case, electric field is of r distance. For a point outside, there will be 3 points we can find electric field, one inside, one on the surface, and one on the outside. Outside, suppose the distance r, we can make a sphere like this, a Gaussian sphere like this, and we can apply the Gauss's law. Electric field will get is how much? 1 upon 4 pi epsilon naught q upon r square. Have you seen this equation earlier? Yes, for a point charge, electric field is the same. So what can we conclude? For a point outside a charge sphere, we can treat the whole charge sphere as a point charge, and the point is considered the charge is considered on the center. We can treat this whole sphere as a point charge. The charge is on the center of the sphere, okay, because the two equations are equal. For the surface it will be same, that is again, okay, that r is small r will replace by capital R. But the thing in the inside, for the inside, how much will be the flux inside? Okay, the electric field is outside only. Charge is outside. Electric fluxes, electric field are in this region. So how much is the electric field inside? Just remember, inside a charge sphere, solid sphere, conductor is, okay. Electric field is 0. For a shell, the electric field is 0. Okay, electric field is 0. So there is no flux inside. If there is no flux inside, then there is electric field is also. From this derivation we can think it the both the ways, because the electric field is 0, the flux will be 0. The flux is 0 because there is no electric field, the electric field will be 0, okay. Why, and what the question is why, and then that is a very important result actually. Inside a shell or a charged conductor, solid electric field is 0, okay. So what happens, a system with charges try to have minimum potential area. They want to uh, get minimum repulsion, okay. So they will arrange and maximum distance from each other. Maximum distance, if it was a solid sphere, they will try to arrange on the maximum distance on the surface, so that the repulsion is minimum. जितना दूर हो सकते हैं उतना फैल जाएंगे, okay. They will try to move as away from each other as they can, so to avoid, to minimize repulsion. You see, electric field due to this charge will be in this direction too, okay, and it is being cancelled out by this charge. Due to this charge is this been cancelled out by this charge, okay. So every charge, the electric field due to one charge is been cancelled out the as counterpart here. So the effect is the net electric field on this whole sphere, inside the sphere, it is 0. It is 0. Inside the electric charge conductor is 0, and this result is very useful. Suppose there is lightning and you have a car. Where is the safest place to be in this lightning? Yes, inside the car. The car is a conductor, so inside electric field will be 0. It will be the safest. We can even protect some of the appliances uh, which may be affected by electric field. What we can do, we put it in a metal case, closed metal case, and inside the metal case electric will be 0. Even you can do an experiment, okay. You try to call your phone with another phone. Now wrap a metal aluminum foil around the your phone. Now try to call. You will see that it is the call is not happening because the electric field, there is no electric field, and signals are electromagnetic waves, so it will not reach inside the aluminum field coil foil. Okay, I think I have spoken enough. Okay, I have one quantization remains, that is not very hard. Q is equal to any charge can be expressed as the fundamental unit of charge, basic unit of charge, integral number. Okay, that is basically, if any charge, it is 20 coulomb, it is some number, it will be a very big number times the fundamental unit charge, that is 1.6 10 to the power minus 19. This is the, and for microscopy it is significant. For big at microscopy level, this is very small number. Okay, so we can take it continuous, that is the quantization charge. Okay, so I think so this was my attempt experiment to teach you like this. Okay, I didn't thought that I will make this much big video. Okay, so if you like this video, please give it a thumbs up and subscribe to my channel. Give your feedback what I can improve. You want this kind of video? If you want more videos like this, please mention in the comment section. And lastly, thanks for watching.